Chapter 8. The last chapter that we completed before we made our jump to trig was chapter 7. So we're kind of picking up where we left off before we took a break to do our trig stuff. Chapter 8 is about exponential growth and exponential functions. This is what the graph of an exponential function looks like. An exponential equation, so the equation that would give this graph would be y equals 2 to the power of x. This is different than x squared. We studied x squared stuff before. When we do x squared, the exponent is a number, or x cubed, or x to the fourth. That exponent is a number. With exponential functions, the x is the exponent. The variable is in the exponent place. The phrase exponential growth gets thrown around a lot on the news especially. They'll say that things are growing exponentially. And when they say that, what they mean is it's growing really fast. Because this is what an exponential growth function looks like, is it takes this rapid turn and then begins increasing quickly. Now, whether or not all of the things they say that about could actually truly be modeled with this kind of a function, probably not. But when we hear the phrase exponential growth, what people mean is it grows really fast. In math, what it truly means is that it's in a function where the variable is the exponent. So today we're going to look at how to graph those. The graphs have an asymptote, which is a line that the graph approaches but never quite reaches. So it's going to get really, really close to it but never touch it or cross it. Some properties of it, it's going to have a y-intercept at the value that is in the front of the equation, or the front multiplier is going to give us our y-intercept. The x-axis is going to be that asymptote that we're going to get really close to that x-axis but not touch or cross it. Our domain is going to be all reals because we could plug in any number we want for x. We might get extremely large numbers, so big that even computers couldn't really process what they were, but it's not breaking any math rules to plug in any values of x. So the domain is all reals. The range will be limited by that asymptote, though. We're only going to get an upper half or a lower half graph. Whenever we explore new functions, a good way to explore them is with xy parts and figure out what happens. So that's what we're going to do here. In our chart, I'm going to use negative 1, 0, 1, and 2. If I plug in negative 1, I have 1/2 times 3 to the negative 1. So now we need to remember our exponent properties. What does a negative exponent do? Turns it into a decimal, or what's another word for a decimal? Another form? A fraction. It turns it into a fraction as what? The reciprocal. A negative exponent makes a reciprocal. Chapter 7 was all about those exponent properties, and then we took a break from those to go on to trig, so we have to kind of jump back and remember those exponent properties. That a negative exponent makes a reciprocal, so it's going to flip over that 3 to make it 1/3. Multiplying gives 1/6 then. When we plug in 0, what is 3 to the 0?
3.
It's not 0. 3 to the 0. We had an exponent property of anything to the 0 power is the same thing. It's 1. Anything to the 0 power is 1. So that gives us 1/2. When we plug in 0 in our chart, you will always get that front multiplier. When I plug in 1, 1/2 times 3 to the first is 3/2 or 1.5. When I plug in 2, 1/2 times 3 squared is 9/2 or 4.5.
Is it okay to get decimals for this?
It's fine to get decimals because what we're going to do is plot these points on our graph. So if you think better in decimals than fractions, decimals are fine. So now we're going to plot these. Back negative 1, up 1/6, which just means a tiny amount. Don't worry about perfection on a 6 there. 0, a half. 1, 1.5. And 2, 4.5. And we can see that by then the graph has made that rapid turn. For our graphs, we're going to follow the x-axis, not touching or crossing it, and then catch all those points, and it'll make that rapid turn upward. The graph should get arrows on both ends because they do go on forever in both directions. Questions? All right, so we're going to make an XY chart once again with negative 1, 0, 1, and 2. When we plug in a negative 1, what did we say a negative exponent does? Reciprocal. So what do we get? 2/3. When we plug in 0, what did we say a 0 exponent does?
1.
Gives 1. And there is no front multiplier here, or we can think of having a front multiplier of 1. So plugging in 0 always gives that front multiplier. And if there is no front multiplier, it's really a 1.
3 and 4 points every time.
You don't necessarily need to graph all 4 if all 4 won't fit. So if the numbers are getting extremely large, then you don't need to. But typically 4 points will be a good amount to begin to see that turn.
So, never mind.
Will the negative 1 always be the reciprocal?
Negative 1 will always make a reciprocal.
Then
Yep.
is why on the last one was it 1/2?
Because there was a 1/2 in the front of the last one. So it made the reciprocal of the 3 and made it into a third. But then we had that 1/2 in the front of that. When we plug in 1, what do we get? 3 over 2. Something to the first power is just itself, so 3 over 2, or 1.5 if you graph decimals better than fractions. And when we plug in 2, how do we square a fraction?
Times by itself.
Multiply it by itself. So if I multiply 3/2 by itself, what do I get? 9 over 4, or 2.25 if you think better in decimals.
Why is that 1 and not equation not 0?
Because 0 times anything would be 0. So just like if we have x, we assume that it's 1x.
It's a multiplication. Got it.
Right, so the coefficient is 1 because it's a multiplication, yeah.
I'm just really confused how you got all of the numbers in like the y spot.
By plugging in the numbers in the x spots to the equation for the
It
x.
looks just so much different than what we did for the last.
If I plug in negative 1, well, in the last problem I showed all the work of plugging it in.
So you just okay.
But if I plug in a negative 1, I would have 3/2 to the negative 1, and a negative makes the reciprocal. So that gives 2/3.
Okay.
So I just wrote down the answers here instead of writing down all the work.
Okay.
But the same process, just plugging those x's in to the equation to get the y. We're going to plot these. Negative 1 up 2/3. Over 0 up 1. Over 1 up 1.5. And over 2 up 2 1/4. And this one didn't really take as sharp of a turn. It's still going to follow that x-axis, and it's still going to catch the points, but it's not getting as steep. The bigger the base is, the more steep the graph will be. And the base is the number that has that exponent. So in the last problem, our base was 3. In this question, our base is 3/2, or just 1.5. If the base was 1, our graph would be a completely straight line, because 1 to any power is 1. So that would just be a straight horizontal line if our base was 1. And then as we get bigger than 1, the graph will become more and more and more steep. So 1.5, not that much bigger. So it's not going to be very steep. Whereas after we get to 3 and 4, those graphs are going to get pretty steep.
All right. So does the graph on the left side does that always start at just 0?
On the left side, our graph will always have the asymptote at the axis there. Yes. Right. Go ahead and try graphing out this next problem. So I make my chart, -1, 0, 1, and 2 as before. When I plug in a -1, it's going to turn that 2 into a half, making the reciprocal, and a half of 2/3 is 1/3. Plug in a 0, and it always gives you the front multiplier. Plug in a 1, and I'll have 2/3 times 2, which is 4/3. And plug in 2, and I'll have 2/3 times 4, which is 8/3. Then I want to plot those. -1, 1/3, 0, 2/3, 1, 4/3, and 8/3 is 2 and 2/3. So we can see it beginning to make that turn. Put arrows on both ends because it does go on forever in both directions. So again, with the steepness, the bigger the base, the steeper the number. 2 doesn't seem like a very big number, but it actually still starts to create a pretty steep graph. We'll make a chart here as well. When I plug in -1, I'm going to have -2 times -1 is going to take the reciprocal, so times 1/2. -2 times 1/2 is -1. When you plug in 0, you should always get the front multiplier. So you get -2. When we plug in 1, we'll have -2 times 2, which is -4. When we plug in 2, we'll have -2 times 2 squared, or -2 times 4 is -8. So when we plot these, -1, -1, 0, -2, 1, -4, -8's off the bottom of our grid here. Our x-axis is still our asymptote, but in this time, it creates kind of an upper boundary to our graph. Why do you think this graph turned out below when all of the other ones turned out above? Because the front multiplier was negative. When we have a negative front multiplier, we are going to get a below graph instead of an above graph. Okay, so we can tell by our equation that it might be really steep or not so steep based on the size of that base. And then we can tell whether we're going to get an upper or lower by a negative or positive front multiplier. We are also going to look at how these graphs can shift around. The nice thing about shifting functions is all functions follow the same rules. So we've talked about shifting rules before, most recently with trig graphs. What does adding or subtracting something to the x do? Opposite way, and is it up or down or left or right? Left or right. It's a side-to-side shift like our x-axis, and it goes in the opposite way of the number. And then what does adding something to the general function do? Moves it up or down based on whether it's a positive or negative. And that does what it says. So in our graphs, the first thing we're going to do is take care of this shifting. So that -1 that's up there with the x, what's that going to do to our graph? Push it to the right one spot. And what's the -4 at the end going to do? Down 4 spots. So I'm going to go to the right one and down 4. And that creates a new center to our graph. Where those two lines intersect is now the new center of our graph. When we make our chart, we're going to make our chart for only the parts of the equation that we have not yet dealt with. So we didn't do anything with the 3, 2 to the power of x, but we took care of -1 and we took care of -4, so we don't need to consider those in our chart. So our equation now looks exactly like our first group of equations, so making our chart is going to be the same process. So when I plug in a -1, it takes the reciprocal of that 2, so it makes it a half. 3 times a half is 1 1/2. Plugging in 0 gives the front multiplier of 3. Plugging in 1, 3 times 2 to the first is 6. Plugging in 2, 3 times 2 squared. 2 squared is 4 times 3 is 12. Then when I plot those points, we are going to plot them from our new center, from the shifted origin, not from the actual origin, but from where those two shift lines intersect each other. So from there, I'm going to go back 1, up 1 1/2 for my first point. Over 0, up 3. Over 1, up 6. And up 12 for the next point. So when we plot our points, we are going to do so from our shifted lines, not from the true origin. Then, instead of our x-axis being our asymptote, because that would look kind of weird here, our graph would have to take a weird twist that it hasn't been doing before, our asymptote is going to be that shifted horizontal line. But we will still have an asymptote, so you should still approach that line but not cross it. Questions on the graphing process? We are then asked to find domain and range. Domain talks about appropriate x values. This graph points directly to the left, so it definitely goes on forever to the left. It's standing really tall over on the right-hand side, but it's always still moving over a little bit. It's moving up a lot faster than it's moving over, but it's always still budging over a little bit. So eventually, the entire x-axis would be covered, which means our domain is all reals, and it always will be for exponential functions. We could plug in anything we want to that x position. I could do 2 to the power of 1,000,000 if I wanted, theoretically. Computers can't even calculate that, but it doesn't break any math rules. So our domain will always be all real numbers.
What about the step
Underneath the x-axis, we're looking at a y value, because that's an up-down. So that means that our range is going to be limited, because our range is what talks about our y values. So our domain will always be all reals, but our range is going to be limited.
Her range is the low part of the range.
So our range is the y values that we can plot on our graph. So y is bounded by that asymptote. Is it above it or below it? Above it. So y is going to be greater than, where is that value that y is not going to quite make it to? -4. That asymptote bounds off our y-axis. We are never going to get anything below -4 along our y-axis. We're also not actually going to get -4, so we don't want an equal to bar here. It gets really close to it, but it never actually touches it.
So it's like whatever point the y. I'm confused as to how do you tell if you don't have an up-down shift.
If you don't have an up-down shift, then that asymptote was just occurring at the axis. So then that would be at our 0 line. So y would be greater than or less than 0. So all of our first examples didn't ask for it, but it would have been at 0 line then. So greater if it's above and less if it's below. But they all have a boundary line somewhere. We'll do this next one together as well. What does the -2 do? Right 2. What's the +1 do? Up 1. So in our graph, we are going to go right 2 and up 1 to create our new center. Then we make our chart based on the stuff we haven't used yet. So 2 times 3 to the x. Same 4 values. If I plug in a -1, it turns that 3 upside down, so I get 2/3. Plugging in 0 gives the front multiplier. Plugging in 1 would give 2 times 3 is 6. Plugging in 2 we give 2 times 3 squared, so 2 times 9 is 18. I am likely not going to plot that point, and that's okay. If your numbers start to get ridiculously large, you don't need to worry about that. From our shift lines then, -1, 2/3, not from the true origin, but from the shift lines. Over 0 up 2, and over 1 up 6. Now remember, it's going to follow along our shift line, not the true axis, but where we bumped the axis up or down to. That's easier to remember on problems like the last one, where if we went for the x-axis, it would have taken a really weird twist. Here, it's really common for students to drop it down to the x-axis. So just make sure that you're not following the true axis, you're following the shift line for our asymptote. For domain and range, domain is all reals, because I can plug in anything I want for x. Range talks about our y variable. Is y going to be greater or less? Greater, because it's an above half graph. And what is it above? 1 is where our shifted line is. Go ahead and try the next one. What does the +1 in the equation do? To the left 1 and the -2? Down 2. So we're going to budge over to the left 1 and down 2 to make our new center. Then our equation is just going to do the stuff we haven't dealt with, which is -3 to the x. Now that negative is just hanging out. That negative is not taking the exponents. If that negative were taking the exponents, we would need parentheses there. Without those parentheses, the negative is just hanging out. This is like saying -1 times 3 to the x. Okay? That negative is not a part of the 3 that's taking the exponent. So when we make our chart then, I'll have -1 times the reciprocal, so that's -1/3. The 0 will give me that front number, which is -1. Plugging in 1 gives me -3, and plugging in 2 gives me -9. When I plot these points, I plot them from the shifted lines, not from the original origin. So back 1, down 1/3. Over 0, down 1. Over 1, down 3. And I don't really have room to do the down 9, so I'm not going to worry about it. Follow along our shifted line, not the true x-axis. So then domain and range. Domain will be all reals always, because we can cover the entire x-axis. The range will be limited. It talks about y. Is it greater or less in this case? Less, because it's a lower half graph. And what is it less than? -2, where that asymptote is. Questions? Your homework is from 8.1.